Alrighty, good afternoon, everyone. This is the lecture 11 from our course on quantum computing. And so today we're gonna discuss the hardware of the quantum computers. We will talk about what we need basically to build a reliable, good quantum computer. And in the second part, we will talk more about the first type of a quantum computer, which is photonic one, photonic quantum computer. Okay, but as usual, let us start with the brief recap what we've done last week, right? So last week we discussed the different quantum algorithms. So we started from this Grover search algorithm, and then Deutsch algorithm, quantum Fourier transform, and something else, right? So the Grover search algorithm, the purpose of this algorithm is to speed up the search among like a list of database of some elements. These elements can be different information like names, words, phone numbers, literally any list of information. And how it works, we encode the information into the basis vectors of our quantum computer with the number of basis vectors of 2 to the power of n, right? Where n is the number of qubits. Like if we have 1,000 qubits, this enormously large number of elements we can encode and then search among these elements. Yeah, so the elements encoded into the basis vectors of a Hilbert space, and then this algorithm is based on basically an operation of inversion, which is done by application of the oracle function or oracle operator, right? So the oracle operator is programmed for searching for a particular element. Like in this case, we search for the element 1, 1. The oracle leaves unchanged all elements in the list and flips the sign of just one element that we are searching for. Okay, we know what we are searching for. We just don't know where this element is located. Okay, so the oracle applied to change the sign of this of the elements, inverse the sign, and then we apply another operator, which is amplifier, right? So the purpose of this amplifier is to amplify the probability amplitude of the element of our interest. And applying this operation several times, the oracle amplifier, oracle amplifier, we can locate the element that we are after with with 100% accuracy, basically, in one single run of our computer. And this algorithm boosts the search, basically like speeds this procedure like exponentially. So if for the classical computer it needs n, for the quantum it requires square root of n, and here is the speed up for the number of elements 10 to the power of 4. So basically 10,000 elements at least. And so the quantum computer will do this procedure much faster. Yeah, here is the details. What else? Yeah, we discussed like how it works in general using this vector representation in the Hilbert space, general circuit for this algorithm and so on. Another algorithm we discussed was the Deutsch algorithm. The Deutsch algorithm intends to solve a very specific problem, which is called Deutsch problem, right? And the Deutsch problem is basically to define whether a function constant or balanced. Okay, so it's again a function like this in quantum computing is known as oracle. Not only quantum but also classical computing. It's called oracle. And suppose we have the operator in our quantum circuit that represents the function like this. And the function can be either one, constant or balanced, but we don't know it. Like classically, we need to call to this function several times in order to figure out what's the type of this function. In quantum, we can do this in just one run, calling to the function just once. And a classical like representation of this function could be fake or true, the coin, right? So this what we discussed last time. The Deutsch-Josa algorithm is the n-qubit generalization to Deutsch algorithm for this type of oracle. It's basically the same, but like for the longer string of zeros and ones. We consider this 2-qubit Deutsch algorithm here. Quantum Fourier transform. We dedicated some time to discuss this quantum Fourier transform. We say that just like classical Fourier, fast Fourier transform, which intends to change the basis from one to another basis, which is called Fourier basis, the quantum Fourier transform basically does the same similar operation. Like in classical, when you have a analog signal, which can be like a sound wave. Right now I'm speaking, right, and my voice is recorded by the mic, and then this acoustic card, right, transforms the analog signal to the digital signal. And this digital signal is represented in a form of a table, which is like very easy to save in a memory of a computer and so on. It's much easier to operate with this data. So Fourier transform. In quantum Fourier transform is used as a block, like to other algorithms, like very popular one. And yeah, so this is the circuit that implements the 3-qubit quantum algorithm. This is the inverse quantum Fourier transform. DFT matrix that represents this quantum Fourier transform and so on. So that's what we discussed, right? And particularly for quantum, for our course, we need quantum Fourier transform for the Shor's algorithm. So the Shor's algorithm is the algorithm that allows to factor the large number, which is the product of two prime numbers. Okay, and so we know this large number is a product of two, but unless you know which is one of the, well, unless you know one of these numbers, the inverse operation, like defining the product of these two prime numbers, is extremely difficult, exponentially difficult mathematical problem. If a number is long enough, like 100 digits, right? If you don't know the either number from this product, the classical supercomputer can work on this problem for billions of years. So it's unsolvable problem for classical supercomputers. Of course, if you know one of these numbers, then the problem is solved like very easy. That's this is the principle we use for this RSA type of encryption, right? To protect the information, to send money, like some secure information, documents, and so on. However, there is this Shor's algorithm that, provided that we have a sufficiently powerful quantum computer, the Shor's algorithm will solve this problem, the prime number, the multiplication of prime numbers problem relatively easily, like much faster. Maybe instead of billions of years, like few seconds or few minutes. All right, so that's very important to study this, to define what's the limitations of this quantum algorithm, and on top of that, develop the so-called post-quantum cryptography methods to protect our information against quantum computers, right? And this quantum Fourier transform is a part of this Shor's algorithm. And the purpose of this quantum Fourier transform for the Shor's algorithm is that QFT basically searches for the periodicity in the prime number. So it turns out that the prime number, like a product of two prime numbers, this big number, if you Fourier transform this number, you can find out the periodicity in some. So you'll get a table like this, okay? And if you look at this table, you will notice some periodicity here. Like it starts from 1, then comes from -1, then 1 again, and so on. So there's a period. So if you find a period like that, then you can apply the classical algorithm that allows to find the product of two numbers, provided that you are aware, provided that you know the period. Okay, so yeah, this is how it works. And of course, there are some other algorithms that we didn't discuss, didn't have time. For example, if you watch this lecture from the like last semester, we also discussed like this random walk algorithm. Another one was about the eigen energies of like chemicals, right? So this is very highly actively developing area, how to solve for the eigenstates and eigenvalues of a complex atom or a molecule or even a media. Okay, so this also, the quantum computer is also very useful for chemistry and quantum chemistry. For example, to design some new materials, design new chemicals, design new medicine, new fuel, and so on. So that's a great purpose of the quantum computing, because we cannot solve these problems in a classical way using classical, even supercomputers. The problems are not solvable, not feasible to for classical computers. All right, so this is the lecture 11. So today we discuss how to build quantum computer, and we start from photonics. And the next lecture will be dedicated to microwave quantum computers and the neutral atoms. Okay, people still come. All right. So, but before I start, let me. So, if you are not aware, Jupyter Notebook can be also used as a in the presentation mode, like slides, right? And in order to enable this functionality, what you need just install this RISE library, right? So you just again pipe install RISE, and then when you reload this page, you will get this button here that can turn your Jupyter Notebook file into the presentation mode. That's very useful, right? And also you will get this slide type, like by default you can put slide to enable the content, and you can also save this file as download it as a .js format, which is slides, basically like HTML, but of presentation slides. So it's very useful, like when you do presentations, when you report and so on. Very nice feature. All right, so let us go to the presentation slideshow mode. And yeah, so this is the lecture 11. Why I hear myself? Let me see, because Janet is not muted. Okay, thank you. On top of this, right, even in this presentation mode, you can create a new line and use, like you can even program during your presentation. Like here I created a new cell, right, and then what I can import, for example, NumPy as NP, right, and then for example calculate some, I don't know, sinusoidal function of pi, right? Yeah, NP pi. Yeah, so you even can do like calculations during in the presentation mode. Very nice feature. Again, I refer to a similar lecture from the past, right? So like what I'm gonna tell you today is pretty much discussed there. But yeah, so anyway, you can watch that video as well. So what is required to build a quantum computer? So we talk about in this course we discuss the
Professor, you mute your voice.
Oops, sorry, I click another different. Yes, sorry. So in this course we discussed the fundamentals of quantum physics, starting from the concept of the quantum state, how a quantum state evolves in time, how we represent a quantum state in a Hilbert space, and how we truncate a quantum space, like in a state of a quantum system, to a system with two alternatives, right? And we call this a system with two alternatives a qubit, right? And in this sense, a qubit can be literally like anything that can acquire two distinguishable states. Okay. So the physics, the physical concept, the qubit itself can be of different nature, and this raises the question what type of system we can use to build a quantum machine, a quantum computer. And in fact, there is five items, five criteria summarized by DiVincenzo, right? So today they call DiVincenzo five criteria for a quantum system that can be used as a building block for a quantum computer, right? So the first criteria is as follows. So a well understood and scalable quantum technology. So the well understood means that we can understand, we can describe with great accuracy like a behavior of each building block. Okay, so like hydrogen atom potentially can be used as a building block, because today we know like everything about the hydrogen atom, even like quantum mechanics, then quantum electrodynamics, which tells us even like more about like peculiar details about the hydrogen atom and so on. So the hydrogen atom is great. It would be a great platform, provided that we can control the quantum, the hydrogen atoms. And here is the problem, because the second part here says scalable. So the hydrogen atoms are not scalable platform. Like it's very hard to capture a single hydrogen atom because it's very small and interact very weakly with our measurements and with the hardware, right? So it turns out that hydrogen atom is not a good material, not a good sample for a qubit. And there are other platforms, of course, that are well understood but not scalable well. At the same time, there are many scalable platforms, but like much difficult to control and understand what's going on there. We need both. We need a good understanding and scalability. Here, I would say this scalability is very important, because and it's not only just for quantum, even for classical computers based on novel novel transistors, right? Like single electron transistor and so on. There are many types of electronic transistors recently developed, and of course they can be used to build a new architecture for the classical computer. Unfortunately, all those platforms are not scalable, or they are scalable much badly than this CMOS platform that we currently use for electronic computers today. So scalability and understanding. Another criteria, the second one, we need to be able to initialize each qubit to a known state. Like it's not enough to trap like an atom and excite it by like somehow. We need to know how to excite how to initialize any particular state in this qubit. Okay, this is the second criteria. Another criteria is that the system must keep the quantum state for sufficiently long time. Like if I say I have a quantum system, I know everything about it, I can initialize the state, but it loses the quantum coherence like very too fast. So the system doesn't work because any quantum algorithm is a time, right? It needs time to operate. So the quantum system must contain this, keep the quantum coherence for a sufficiently long time. A universal set of quantum gates. This is a very important criteria. And as we will discuss today, particularly photonics, like the quantum computers that are based on the light, doesn't really fulfill this criteria, because a universal set, as we discussed, for any quantum computer, we need a particular number of single qubit gates and 2 qubit gates. Okay, and in optics photonics, a single qubit gate like very easy to realize. In fact, we will discuss today, it's like even trivial. But 2 qubit gates, it's much more difficult to realize. It's a challenge for the reason we're gonna discuss today. The final criteria says that we not only need to initialize and proceed with the quantum gates, the qubit is supposed to be easily read out, right? So this measurement, we need to be able to measure the result from each particular qubit. So yeah, these are 5 criteria for any arbitrary quantum computer. And here I put together a list of like how many, 6, 7 recent state-of-the-art quantum computers. I arranged them according to the number of qubits. And as you can see, today we have quantum computers with over 1,000 qubits. Let's say like the first time I taught this course was 2021, the year. At that time, we had just roughly around 100 qubits. After three years, we already have over 1,000. And the next step in this growth, in this development, is to reach 10,000 qubits, and that's feasible. That can be done. From this table, you can also notice the platforms, right? Okay, so the largest number of qubits today is done using neutral atoms. Neutral atoms. And then goes this superconducting, basically circuits based on superconducting quantum Josephson junctions. This platform we will discuss, these 2 platforms we will discuss next time. And the last one is photonics. Okay, so photonics, for example, this Xanadu company based in Canada, as I remember. So they have the quantum computer based on photonics with 200 something qubits, optical photonic qubits. So photonics here, photo stands for photon, like elementary particle of light. And photonics and optics, in this sense, are synonyms. Okay, so this is just a computer that based on the principles of light. Yeah, so main architectures are neutral atoms, superconducting quantum circuits, and photonic-based quantum computers. These, their own pros and cons. So there is no perfect platform. Each one gets pros and cons in this or that aspect. Today we're gonna talk about photonics, and the main advantage of photonics is the easy to create a single qubit. Single qubit gates. One. Second, the very large coherent time of the very large time we can keep the quantum state of our qubit, photonic qubit. Like, for example, we can look at the night sky and see this light coming from the very distant stars, like the stars located from us from like billions of I don't know, like light years. Okay, and still we can receive those photons, and those photons came to us, meaning they didn't scatter. So that means that the photon can keep this polarization state or the propagation direction state for billions of years. So it's very long coherence time for the photonics. This is for the pros. Cons, the drawback of photonic-based platforms is the lack of two qubit gates. There are some 2-qubit gates, however, they are not easily scalable. And these disadvantages actually inherit from the advantages. So the fact that photons don't interact allow them to keep the quantum state longer, but unfortunately, this lack of interaction leads to the disadvantage. No scalable 2-qubit gates. All right, so let us talk about photonics for quantum computing. And here we start with the concept of a laser, right? So photonics deals with photons, the elementary particles of light. And the first step is to be able to generate light particles, to generate photons. So yeah, and if you take a laser, the laser can be of different, it can emit the light of different color, like here red, blue, green, and different color here means different wavelengths. So like if we measure the energy of each of these 3 beams, we will find out that their energy is quite different. Okay. At this point, I can also mention that the color not always because of the different energy. Sometimes it's because of the way our eye works. For example, you probably know that we have this pink color, right? But the pink photons don't exist. So pink color doesn't exist in nature. So whenever you see pink, it is a fictitious, it's a artificial color, not the real color. Another example is brown. Brown also doesn't exist in reality. But typically laser emits one single line, which means a photon of a single frequency. Frequency means energy here. And we can detect the photons, single photons. To do so, we typically use this device called single photon detector. So I think single photon detector works pretty, easy to understand the principle. You have a semiconductor crystal. You inversely bias this semiconductor crystal with some amount of voltage, basically. And when just one single photon comes to the crystal, it creates the extra net charge in the crystal. And then this this voltage bias accelerates this extra net charge, and this charge creates other electrons, like 2 electrons, then the 2 electrons create 4, and so on, like a avalanche process. Okay, and finally we can detect some voltage drop across this semiconductor crystal. And for each single photon creates a spike in such a time domain graph as shown here. So each spike corresponds to one single photon. Okay. The key point here to understand is that we never detect a half of a photon. Okay. Especially in linear process, we cannot detect a half of a photon. Photon comes always as a particle. Okay, so the photon cannot be like splitted into two smaller photons or something like that. So when it comes, when we detect photon, it comes as a single particle. And and if we connect this detector to a speaker, we can even hear this clicks, like click, click, click. One click means a photon comes to the detector. All right. So we can generate photons. We can generate photons one by one. If we dim the light beam sufficiently, or if we use some sort of a molecule atom that naturally emit a photon one by one. And we can work with every single photon. And then how we can encode a quantum information into the state of a photon. So in order to encode the information into the state of a photon, we can basically use any physical quantity that can acquire two drastically different states. Okay, one approach is to use just the path, the propagation direction of a photon. Let's say a photon can go left, right, or up and down, like horizontal or vertical direction. That's one way. Photon goes either horizontally or vertically, or both directions simultaneously. When we're talking about like simultaneous process, if photon can go one direction or another direction, the rules of quantum physics dictates us to consider these two opportunities simultaneously, like a photon travels both directions simultaneously. And this is a qubit, right? This is a system with two drastic different states that we can prepare with a certain particular probability distribution. Say 50% horizontally, 50% vertically. Similarly, we can use the polarization state of a photon. You know that light is a transverse wave, right? It oscillates, like electric and magnetic field oscillates in the plane that is orthogonal to the propagation vector. which is wave vector. And in this plane, it can oscillate up and down, either in the vertical direction or in the horizontal direction. So there are two directions for the photon to be polarized, and we can use either one. I mean, we can use this as a state of a polarization qubit. Okay, let us discuss this in more detail. So let us talk about propagation direction encoding first. And here, if you look at glass, like piece of glass, like window, okay, so you of course know that light doesn't propagate perfectly through window. It is partially reflected. Always you get some reflected signal or reflected number of photons. Like if you come to a window in the night, you will see your own reflection, right? So the window always reflects. And of course, one can say, oh, I have like number of photons here. Some photons propagate through, some photons for some reason reflect. And that's okay, but we can continue. We can conduct this experiment and dim the incident wave to just one single photon. And the photons are perfectly identical, like no difference between photons. And then if you look at this simple experiment, you will notice something strange, like a piece of glass that for one photon, one photon transmits through the glass, but another photon reflects from the glass, regardless from the fact that the photons are completely identical. Like how every single photon decides is he supposed to transmit or reflect from, bounce from the surface of the glass. And the rules of quantum mechanics here tell us that for every single photon, we have to consider the both opportunities here. So every single photon, as it gets to the glass, to the window, propagates through the glass and bounces from the surface of the glass at the same time. And we cannot tell which way it went before we measure the photon, here or here. When we measure it, we can say, yes, the photon reflected. Or if we detect the photon here on the right side, we say, oh, the photon passed through the glass. But before the measurement, we have to consider these two opportunities at the same time, simultaneously. It sounds like, or you can consider this as a photon coming to the piece of glass. Then the piece of glass creates like two, like say, two opportunities of photons or two clones of photons. So if you detect a photon, you always detect just one photon. But after this reflection experiment, you consider it's like the window, this glass, creates two clones of the same photon. Okay, if you measure the reflected or transmitted wave, which is like I'm setting many photons one by one, and a number of them came to the right side, another part came to the work it to the right side, and these coefficients, this amount of photons reflected or transmitted, is given by reflection coefficient and transmission coefficient. And let's say if I normalize the initial state of a photon to 1, 0, okay, so this is my 0 state, then this piece of glass creates a superposition of 0R and T0. And yeah, so for example, this first term in this vector, it says the direction of transmission. Like the first one is a transmission from left to right, right, and the second one is like transmission from right to left. So you can encode this information, this state, in the superposition of two states. Okay, so any window, any piece of glass, everything that reflects and transmits light can be considered as the simplest optical qubit, right? So the photon in these two, in the superposition of these two, is already kind of a qubit. So this is how simple it is. Of course, for the computing, we don't use the window, right? We use something more interesting, the element which is called beam splitter. So beam splitter works just like window, but it creates the perfect superposition, the balanced superposition of like 1 over square root of 2 probability amplitude for the photon going to the right, and exactly the same for the photon going to the left. Okay, and this beam splitter, in this sense, is nothing but the Hadamard gate, because Hadamard gate, as we know, takes a basis vector and creates a perfect balanced superposition of two vectors from 0 state to plus state. This is exactly how the Hadamard gate works. So a beam splitter is an optical version of a Hadamard gate. Okay. We can also develop other types of quantum gates. One is like what it is. It's a conversion from one propagation direction to another propagation direction. So it's basically X gate. Like a mirror works as an X gate. So it takes a 0 state and converts it to state 1. From propagation from the left to right, it converts the photon to propagation from right to left, the X gate. The phase shifter, phase like P gate, right? The P gate, what it does, it adds some phase to the quantum state, to one of the basis vectors, to one of the basis states. And yeah, so if you just take a thicker piece of dielectric, like a thicker glass or some silicon wafer or slab, partially the photon will reflect, but another probability for the photon is to transmit through. And while it transmits through this piece of dielectric, it acquires some phase, some additional phase. And we can control this phase by changing either the thickness of this element or refractive index of this element, and so on. So the P gates also easy to realize in the optical quantum computing realm. So, as I said, for the quantum we use beam splitters. In the schematic, we represent a beam splitter by this quadratic, like this rectangle, with a line in there. So this line says that the beam can bounce off from this surface, like, and go vertically, or propagate through the beam splitter in the horizontal direction. accordingly, we can encode this vertical state by this basis state arrow up and horizontal direction by arrow right. Okay, and these two states, of course, orthogonal. If we, because that's obvious. Obviously, they are obviously orthogonal. That's why we can write something like this. For the orthogonal vectors, we can normalize them, these two vectors, to give 1 for the square of their amplitudes. And yeah, so if I consider now like horizontal photon coming to the beam splitter, it creates two, one going in horizontally, another one going upward, and the state in the output of this is the balanced superposition of two, horizontal and vertical, with plus between these two, so Hadamard gate. If light comes from the opposite direction, from this in the horizontal way, again it creates the reflected and transmitted waves. The beam splitter will divide these two probabilities, right? So that's why the same coefficient here, but we get this minus between two elements. That's we instead of plus here. So this minus is because when we use this beam splitter twice in the result, eventually we're supposed to get the horizontal state or the vertical state, basically the initial state. So this beam splitter must operate like a unitary operator, right? That's why if I apply this beam splitter twice, I supposed to get the initial state. That's why we put minus here. All right, so let us consider a structure, a very important one, which is called Mach-Zehnder interferometer. And this system consists of two beam splitters, the input one, the output beam splitter, and two mirrors that convert the horizontal to vertical photon. Okay, so if the first beam splitter receives horizontal photon, meaning propagating in the horizontal direction, it creates two clones, right, of the photon. So it's the photon always just one, but the beam splitter creates two opportunities for the same photon, and this photon can go horizontally this way, or bounce and go to in the vertical direction this way. And before this mirror, the state of the single photon is given by this superposition of two. Okay. Then we can put some sort of a phase shifter. Again, this is just the piece of dielectric where the photon propagates like additional distance comparing to the upper one, comparing to the upper state. Okay, and then using another mirror here and using the second beam splitter, we make the photon interfere with each other. So it's like a single photon interaction. The photon splits into two opportunities, and then the second beam splitter superimpose the two opportunities and creates the superposition for the opportunities, like for the basis states to go either up or right. And it turns out that this scheme, so first of all, if you recall one of our lectures, former lectures, when we discussed the golden single qubit circuit. So this is exactly it. We had two Hadamard gates, one input, one output, and some phase change gate for one of the basis vectors. So this is exactly it, the golden single qubit circuit, but realized in optics. Okay, and if you recall the result, the main result was that if we change this phase of this phase qubit, we can control the probability for the photon to go either way, to go up or to go left, sorry, to go right. And these two probabilities given by the square of cosine or sine. Okay, so Mach-Zehnder interferometer, like a system, like well known for a long time, but if you look at the system from the quantum point of view, it behaves in a weird way, let's say. So when a photon interacts with a photon, and this is, by the way, experimental result. Like people send single photons to this interferometer, recorded the results, and the result was exactly like this. So this result, by the way, also means that if you set this phi to a right angle, like if you set it to be 0, if you remove this gate, right, you will get horizontal photon with like 100%. No, the opposite way, right? So it's going to be upper going photon. However, if you set this phi, for example, to the angle pi, right, the pi, then the photon will go to the right. So you can control which way the photon eventually goes. Then, if you put find like some sort of screen here or here, you will see on this screen a picture like this. So this is called interference pattern. Interference pattern, and what I just said about a photon coming to the up or right means that if I cut only this central part over here, and I detect the photon in the center. Okay, so now, right now, for this picture, we have no photons coming to the center, and this can be one of these states when the photon goes the other way. If I change the phase slightly, I will get the bright spot in the center, meaning the photon comes to the central area. And this phase change is defined by the thickness of the dielectric slab, dielectric layer, and also the wavelengths. And the wavelengths of a light is given by a few hundreds of nanometers. Nanometer is 1 billionth of meter. So it's a very, very small, tiny number. And that means that if we change this phase just by a little small amount, we can create a drastic difference, like no photons or more photons in the experiment. So we can use a system like this for a quantum sensor. For the quantum sensor. And in fact, this type of interferometer, Mach-Zehnder interferometer, is widely used for sensing and quantum sensing. All right. Nanometer resolution. Let us look at this system now and put some absorber. absorber here means that we detect a photon. Like we absorb photon, and we can create this photon into the pulse of a current, like in this single photon detector we just discussed, or it can be absorbed by some material and convert into heat, right? So it will heat up this area on the absorber just a little bit. So anyway, this absorption means that we detect photon there. Like if we initially had this horizontal photon, then the photon splits into two possibilities. And then if we put this detector here, it means that we observe the photon. If we don't observe the photon, here, it means that the photon went up. So it's still detection which way the photon went through this first beam splitter. And putting another beam splitter here will make the result that 25%, perfectly 25% of all photons go either up or right. And we cannot control this. So in this experiment, the photon behaves as a particle. Okay, so if we look at the system, if we detect the photon starts behave as a particle. If we don't look, if we don't observe what's happening there, in that case, the photon behaves as a wave. So that's why we have this particle wave duality. The concept you probably you of course aware of. Yeah, but if you remove this absorber, we now don't know which way the photon went through the first beam splitter. We have to consider these two options simultaneously, and these two options, these two opportunities, interfere in the second beam splitter and get another, and this leads to another result. Like for example, in this case, 100% of photons going to the vertical direction. Okay, so comparing to this one, where the probability is fixed to 25% of the photons, here 100% of photons go up. This result is known as a so-called Elitzur-Weidmann-Bomb thought experiment. Okay, so if you take the Mach-Zehnder interferometer, just like the one we discussed, and consider a toy bomb, okay, bomb with a detector in there. And I say that the bomb is defective if I have no detector there. So if a photon can pass through the bomb like this without being detected by the probe, this detector is indicated by the star here, then the bomb is defective. However, if the detector is there and the photon can be absorbed, then I say that the bomb is good. Okay, and then we say that we have some large number of these bombs, and I need to figure out if the bomb is good or defective. Okay, and the question is, can we do this analysis like optically without like a bomb being exploded, right? Without exploding the bombs? And the answer is yes. If I consider a bomb like this, put in this Mach-Zehnder interferometer, then if I get, for the perfect case, sorry, for a good bomb, sorry, for the defective bomb, the photon, one single photon goes this way, vertically, and then bounce off from the mirror. And the second opportunity for the bomb, for the photon, goes through the bomb without interaction because the bomb was initially defective. Okay, and in this case, I will observe, let's say 0% in the of photons that going to the right in this horizontal direction. Okay, so if I put a bomb in there in the experiment and I observe no photons, that means that the bomb is good. Oh, sorry, the bomb is defective. However, if the bomb is good and the detector is there and detector is functional, there are two options here. One is that initially the photon went through the upper path, right? Or photon went through this lower path and detected by the detector and the bulb exploded. But for a number of experiments, we will get 25% probability for the photon that goes vertically and horizontally. So in simple words, if we observe a bomb, if we don't observe a photon here in the horizontal direction, the bomb is defective. If we observe a photon, the bomb is good. So this is, I mean, this type of experiment never been done with bombs. I don't know why they use these bombs and so on. This experiment has been done in experiment with optical detectors, right? So if you put an optical detector here, and again, the photon either goes through or absorbs, the rest of the logic is exactly the same. So this experiment has been done, and the results confirm this logic. Okay, so in other words, we can detect something without interaction with it. Like we can detect either the bomb is good or not, even without interaction with the photon. This is very interesting fact, like very interesting, philosophically interesting fact. Anyways, yeah, and maybe the last thought on this picture is that today we use the so-called ghost microscopy. Okay, when we create the photons, and they can go to different ways, and one interacts with something like a tissue, like biological, with something, with some material, and another path doesn't interact, and we detect the one that didn't interact with with the matter, and we can observe the effect that this matter produces on the light beam that never interacted directly with the substance, with like live tissue. So it's called ghost microscopy. But for that experiment, we use so-called entangled photons. But the concept is very simple to this one. Anyways, so this is the first type of encoding of information into the quantum information into light. Do you have any questions about this part while I'm drinking some water? Okay. The second approach is to encode information into polarization state. And here is the picture, the classical picture of a light in the wave representation. Okay, so light and any single photon, it gets two parts, like two fields associated with it, right? Electric field and magnetic field. And the electric field and magnetic field, they oscillate in the direction orthogonal to the propagation direction, so to the k vector. And the fact that light is polarized can be absorbed easily using a device called polarizer. So a polarizer is a system that allows light to propagate with a particular polarization direction. For example, this polarizer on the picture allows light, which can be initially polarized in all different directions. For example, it can be like a sunlight, where the polarization of the photon is not fixed or is not defined. So the polarizer allows just only polarization that aligns with this polarization axis, okay, to pass through. And it blocks, either reflects or absorbs the all other polarizations. Okay, so the polarizer. A simplest version of polarizer is a slit, like a narrow slit in a screen. Okay, like if the polarization direction is set along this slit, the wave passes through the slit. If it's polarized in the orthogonal direction, like this red wave, it is blocked by the polarizer. So the polarizer is set to select just one polarization, okay? And then we can put another polarizer, which is called analyzer. If you put the analyzer in parallel with the polarizer, then the wave will pass through the analyzer without changing the wave. However, if analyzer is set orthogonally to polarizer, it will bring the vertically polarized wave, obviously, right? So we can set these two polarizers, analyzers, and play around with the polarization of light that passes through the system. And here is the same picture, but in the quantum, in the notation we used for quantum, right? So let's say we have a wave that is partially polarized vertically, V, and horizontally, H. So the horizontal polarization here must be drawn like orthogonally to the vertically, so it must be drawn like this. But for simplicity, I just put this arrow like along the propagation, so it doesn't really matter. So this is the horizontal polarization of a photon. And then here is the polarizer, which is set vertically. This vertical polarizer allows for the vertical polarization pass through. And another one, which is analyzer, again allows this vertical wave pass through. So we got some only vertically polarized wave in the output. However, if I change the analyzer to the horizontal one, no wave will pass through this system because the analyzer blocks the vertical polarization now. Okay, but what if I set polarizer at the angle of 45 degrees? like shown here. In this case, the vertical photon can pass through the polarizer, but with the probability of 50%. And also this polarizer can convert the vertical to the horizontal, again, with 50% probability. Okay, so if I rotate both the polarization of this wave and polarizer back by 55 degrees, so this in a new coordinate system, right? The polarizer will be oriented vertically. Then this vector v will be oriented at 45 degrees, and again, the polarizer will either create vertical or horizontal wave for this initial state. And this is exactly how this Hadamard gate works. So a polarizer set at 45 degrees operates as a Hadamard gate, and it creates the balanced perfect superposition of vertical and horizontal states. This is like a simple version of a Hadamard gate. In fact, this is a transparent crystal, okay, with some amount of optical anisotropy. So the optical anisotropy is the property that when a light travels with slightly different speed through the crystal. Okay, so the crystal not homogeneous; it is anisotropical. The wave propagates through the crystal with slightly different speed. And when light comes to this crystal, it splits into two waves. One is ordinary wave that propagates without change of the polarization. And another one, the polarization here is along the axis of the crystals. It's not important for this picture. And another wave. And this another wave gets orthogonal polarization. And the result of these two waves, the superposition of these two waves, creates the polarization of different angle. Okay, so let's say if these two waves, ordinary and extraordinary, propagates the same, if they acquire the same phase, then the resulting wave will be polarized at 45 degrees. This is exactly what Hadamard gate does for the qubit. However, if they propagate a different distance, they get different phase, then we can get other states, like shown here. For example, sometimes when for a particular thickness of a crystal like this, the crystal can, as I said, create the 45-degree polarization in the output. For example, from the input vertically polarized wave, we create 45-degree output wave. And this is what we called a half wave plate. And this half wave plate works as a Hadamard gate. For vertical, it creates state plus. However, if we change the thickness of this plate, namely if we make it twice smaller, we get another device which is called quarter wave plate. And this quarter wave plate creates the circular polarization, either clockwise, like shown here in the picture, or counterclockwise. And as we remember, this clockwise polarization is given by V plus imaginary unit H, which is exactly plus I state. So such a quarter wave plate creates state plus I, which is another type of gate, mainly P gate, right? So the dielectric with some properties like anisotropy allows to control the state of such a polarization-based optical qubit. So yeah, using such optical elements, we can control optical qubits, and we can create single photon gates. But that's not enough for universal quantum computer, right? For the universal quantum computer, we need 2 qubit gates. When one state of one qubit, when one qubit interacts with another qubit. And unfortunately, light doesn't interact with each other. Like you can take 2 laser beams and then cross it, and you will see nothing, right? The photons don't interact. They just pass through each other like through empty space. Unless we have strongly nonlinear system, okay? That's why we need nonlinearity. We need a medium that is strongly nonlinear to enable photons to interact. And only this way we can achieve the 2 qubit gate functionality, okay? And this is one example of such a qubit, the most important one, optical C-not gate. I took this from this science paper. So effect is the idea is very simple. So we have 2 photons. One photon can travel it along this path, which we call 0, or this path, which we call 1. Okay, and the target qubit, the target photon, which can travel this way. So here and here we put a beam splitter. So right when 0 photon, for example, here in the target comes to this part, it can go either this way or this way, and the same for the first for the photon in the state 1. And yeah, and the key element of this scheme is this nonlinear phase shifter. So this is basically a strongly nonlinear material which depends on which behavior depends on whether we have the photon in the control part of this circuit, photon coming to the state 1 or not. So you remember that control not C not gate state of the target qubit depends on the state of the control qubit. When it's 0, then the target qubit does nothing, right? So it keeps the state of the target photon, of the target qubit. However, if the photon in the control qubit comes to this nonlinear phase shifter, it enables, so basically it provides sufficient amount of intensity that creates the nonlinearity for the target qubit, and it controls the output in the target qubit. Okay, so this is how it works for 2 qubit gates, photonic 2 qubit gates. It works. It was realized in experiments. Unfortunately, this scheme is not scalable well. Like if you put another qubit like this, okay, you can achieve similar functionality, but this nonlinearity, I mean, this output from the first one won't be sufficient, likely won't be sufficient for the second gate like this, and so on. So yeah, this approach is not very scalable. Definitely not scalable to the hundreds or thousands of 2-qubit gates. In quantum photonics, in quantum computing, optical quantum computing, we also have the opportunity or approach to create the Bell states. So you remember this perfectly entangled states, non-separable states, which we call Bell states. And in fact, this was the first system where these Bell states were realized, and the people who use this approach for entangled states generation and so on, they recently got this Nobel Prize for this study. So what is this about? So let's suppose we have a crystal. This crystal is strongly nonlinear, and specifically it gets second order nonlinearity. Okay, so it's just one type of optical nonlinearity. And what happens is that this laser beam, typically of high energy, like blue colored light or green light, it comes to the crystal, and inside of this crystal, the photon, this green photon, can spontaneously be splitted into two photons of smaller energy. Let's say the green photon is splitted into two red photons, right? And here we have this momentum conservation, basically, which states the fact that the vectoral sum of the products of these two vectors must give us the vector which is propagation direction of the initial of the pump photon. So momentum conservation and energy conservation. Energy conservation is simply that the fact that the frequency of the initial pump beam must be equal to the sum of the products. Okay, and this momentum conservation and energy conservation imply that these two generated photons will be entangled. Meaning, if we detect one, we immediately know everything about the second one, and so on. So this process is called spontaneous parametric down conversion, and it's very important for quantum photonics and optical quantum computing. In order to give you an idea how photonic quantum computers look like, this picture presents an optical table with the optical breadboard, as you can see, and each of these elements here represents different optical elements. Like, for example, here in this array here and here, you can recognize these beam splitters, these cubic elements, which are beam splitters. Some of these elements are lenses, irises, and so on. Many different elements. There is an input here, output that comes to the single photon counters arranged here. So this is how a system like this optical quantum computer looks like. So this is a system of 76 qubits. This system is called, it has been proposed recently, realized recently by a Chinese group, and this system is called JISHANG. JISHANG. Yeah, this is the name of the system. Yeah, so the important fact about this system is that the system is completely linear. So it uses only single qubit gates. And the purpose of the system like this is to do an operation which is called boson sampling. This is just some sort of statistical manipulation with the photons or array of photons. So it's not very practical problem, but still not solvable by a classical computer. Okay, so these professors claim 100,000 billion times faster than the current supercomputers. There were and there is some strong debates about claiming numbers like this and so on, but anyway, the system works. This is not universal quantum computer because for the reason I described, right? No two qubit gates on the system. The current state of the art and the current trend is to push the complex system like this on the surface of a chip. Okay, because when you scale down everything, typically nonlinear effects get stronger, and you can expect to achieve two qubit gate functionality on the surface of a chip. And of course, on top of that, we always strive to make the photonic elements more compact. So yeah, putting everything on a chip like shown on the right, reported relatively recently, like 2-3 years ago. Okay, and when we scale down the optical elements, on a chip, we come to the realm of nano, right? Nano photonics. So we interested in different effects of light matter interaction with the matter at the nanoscale, like light interacting with some nanoparticles and so on. And in fact, there is a lot of fascinating, interesting, promising effects appear when you study a system like this, light interacting with nanoparticles and nano devices. And this is a current trend in optical quantum computing, whether we can achieve quantum functionality like two-gate optical computing using quantum approach. There is a very interesting approach here associated with coupling light to strongly nonlinear materials like these two-dimensional materials. When light interacts strongly with matter, we have no more light and matter. The light and matter hybridize and form a new type of particles, which are called excitons or exciton polaritons. So these particles are neither light nor photons. Oh, sorry, neither light nor matter. It's a hybridized state, and these hybrid states of light and matter are particularly interesting for quantum computing, optical quantum computing, because these particles can interact and can form entangled states. So it's much easier to create 2-qubit gates of these exciton hybrid exciton states. Okay. Do you have any questions about this part? Okay, so this brings us to the conclusions. So today we discussed the criteria, this 5 criteria to for a quantum system that can be used as a building block for universal quantum computing. And universal quantum computing means sufficient a number of gates, single qubit gates, 2-qubit gates, in order to be able to run like any arbitrary quantum algorithm. Photons offer a number of advantages. Of course, photons travel at the speed of light. The speed of light is the fastest in nature. We can control light, manipulate light. Today, we easily generate light, even down to single photon level. We detect light with quite high efficiency, reaching 90% and 90% and so on. All this makes light very promising platform for quantum computing. Unfortunately, photons don't interact with each other unless we have strongly nonlinear material, media. That motivates researchers around the globe to design new materials that have as strong optical nonlinearity as possible. So we need strongly nonlinear optical materials. Yeah, for example, in my lab, we've done quite a few works on this topic and so on. Another approach is to couple light to matter, form excitons, and so-called strong coupling regime of light and matter, and use those new type of particles, which called quasi-particles, to achieve this strong nonlinearity on the single photon level. Yeah, so this all makes photonics and quantum photonics very promising for quantum computing applications. Another, by the way, point I didn't mention is wide use of quantum optics for other quantum technologies, including quantum cryptography. Right, so today, quantum cryptography is pretty mature area. We use quantum cryptography for different purposes. Banks use quantum cryptography to share information and so on. And pretty much all of those systems based on photons, based on the fact that light propagates without dissipation in an optical fiber. Okay, so all this makes this platform very promising for quantum computing, and I bet it will develop much more as the time passes. And so here is the list of some materials for future for more read. Right, here I put some like good review papers on quantum computing in general, optical quantum computing. I put some links to these companies that work on these optical quantum computing problems, not only computing, not only photonic, but also these neutral atoms, and so on. Yeah, so this is it for today's lecture. Next time we will discuss in depth about superconducting Josephson junction qubits and neutral atom based qubits. And yeah, so thank you very much. And let me stop the recording and then we can discuss.